This video is on cascade amplifiers. In other words, cascaded transistor primitives. So in a cascade, what we mean by that is that we take gain stages and cascade them together in series. So we can start with a source, and that feeds the input of a first gain stage. Then that gain stage feeds another stage, and that other stage feeds yet another, until we finally feed and drive a load. So what we can do is each of these gain stages is basically a transistor primitive, a common emitter or a common gate or a follower. So what we'll do to analyze this is that we'll replace each of these gain stages with its equivalent two-port network. So again, here we have the source, and that feeds our first transistor amplifier that has an equivalent input resistance, short circuit transconductance gain into an equivalent output resistance. And that drives another stage. And that other stage also has an input resistance, transconductance gain, and output resistance. And this way we can have many amplifiers cascaded in series until we have the last amplifier here, which will then drive the final load. So when we do the analysis, basically, let's say we wanted to get the small signal gain translation from the input voltage to the output voltage. So in this circuit is all the way from the input to all the way to the output voltage. What we do is we do the gain of each stage and cascade them together. So first we have the small signal translation. Let me remove markers here. First we'll have the small signal translation across the first gain stage. That will drive the second stage, and we have the small signal gain translation across the second, then the third, fourth, until we finally have the gain translation across our last stage. And each of these gain stages will then be the two-port equivalent gain, which is the short circuit transconductance current into the combined load resistance. And that's what we see here. I'll circle it so it can be more explicit. So then we have here for the first gain stage, we have the short circuit current feeding the combined output resistance. And then that's again across the first stage. Across the second stage is the subsequent short circuit gain transconductance into its combined output resistance. And like that, we can do each of the gain stages. One thing that I want to highlight here, and I'll remove markers here so we can see it more readily, is that we're actually including the loading effect of each gain stage, because the input resistance of a subsequent stage loads the output resistance of the first stage. The combined resistance is the one that basically sets a gain. So by including the effect of that input resistance, we're basically including the loading effect in our gain. And then all the way at the output, we have the load resistance will then also affect the gain of the last gain stage by basically loading the output resistance. And that's what we have here. Each of these parallel combinations, we can actually just call them by an equivalent resistance. So if we go out here and remove markers, basically at each intermediate node we have an equivalent resistance to ground, and it's just a parallel combination of all the resistances that we see there. And that's what we can call R1 for the resistance at the output of the first gain stage. For the resistance at the output of the last stage, then it would be the load resistance in parallel with the output resistance of the last stage, and that's what we'll call the output resistance of the overall circuit. But we can also get other gains, and let me remove markers here. So if instead of having the voltage gain like we have here, we can also get the transconductance gain, the small signal translation from the input voltage to the output current. In this case, then, it's the input voltage all the way on the left, but in this case, we're interested in the output current, the current that feeds the load resistance. So again, we divide and conquer. And the first thing that we can do is we can do first the voltage gain translation, small signal translation, from the input to the output. And that gets us all the way out to the output voltage here, the one that is across the load. And then we do a small signal gain translation from the output voltage to the output current. But we know the gain translation from the input voltage to the output voltage is basically the voltage gain that we just did in the previous step. So we can use that, and then we know that the small signal translation from output voltage to output current is nothing but the ohmic translation across the load resistance here. In other words, the output voltage divided by that resistance will give us the output current. And that's what we have here is 1 over RLD. So again, we can get another gain in any gain we desire. And basically, this just shows the usefulness of two-port networks, because once we take each transistor gain and we map it out into an equivalent two-port network, then we can apply the conclusions of the equivalent two-port networks to then get the gain of the overall circuit. One last thing I will say here is that we can use capacitors to couple stages together, and we'll see this in an example in the next slide. We can also use capacitors to remove the effect of resistors. But let me just show that by way of an example. So here we have an example, and what we have here is transistor gain stages. But let us make a few notes before we translate this into something we can analyze. First, we use resistors to bias transistors. So RE1 sets the emitter voltage of the first transistor, RC1 sets the collector voltage, and R11 and R12 set the base voltage. By setting all three voltages, we can actually control the current that flows through the transistor, as well as the voltages that bias the transistor. So this is how we bias the transistor. These resistors will ultimately also help set the gain, because across this transistor here we can replace it with its equivalent two-port network because it's a gain, and the resistors will then load the input and the output, and they will therefore help set the gain. Then we have capacitors, and let me remove markers here. And we can see, for example, that CS, it couples source signals into the emitter of the first transistor. And C1 couples signals from the output of the first transistor into the input of the second transistor. And C2 similarly couples signals across stages. And CO also couples signals from the source of the last transistor into the load resistance. We also have capacitors that basically shunt away the effect of resistors. And CE2, for example, here, it basically shorts the effects of RE2 at higher frequencies. And that way it can remove the effects of RE2 at higher frequencies. However, RE2 is still, nevertheless, used to bias the transistor at low frequency, at DC. But as we apply small signals at higher frequency, then the effect of that resistor disappear because CE2 shunts it away. So let's remove markers here. And we're going to apply two concepts here. First is what we'll call the short circuit approximation. And what that means is that large capacitors short at low frequency. So what we're saying is CS here shorts at low frequency, C1 shorts, C2 shorts, C out shorts, and CE also shorts, so it removes the effect of this resistor. And then let me put a line here that shorts into the positive power supply. The next thing that we'll say is that the power supply here has no small signal variation. What that means is that the small signal voltage is 0, which is the same as saying that it's basically AC ground. So we can turn this one into AC ground, AC ground, AC ground, AC ground, oops, and AC ground here, and this is also AC ground here. And basically CE2 shunts the emitter of the second transistor into ground. So now we can apply these and redraw the circuit to reveal what transistor amplifiers we have. So RS feeds into the emitter of the first transistor, and that's what we see here. RS feeds into the emitter of the first transistor. In RE1, it's a resistance to ground. That's what we see here. The base of the first transistor sees two resistances to ground in parallel. And that's what we see down here is the parallel combination of those two resistances. Then the collector, we see a whole bunch of resistances to ground. We see RC1, and then C1 is a short, R22 and R21 are all to small signal ground. So the parallel combination of all those, it's at the collector of the first transistor, which is the output of the first transistor. That feeds the base of the next transistor. That's what we see here at the base. The emitter is connected to small signal ground, so that's what we see here. In the collector, we have resistances to small signal ground. We have RC2, R32, and R31. So all those are in parallel from the collector to ground, and that's the output of the second transistor. And that feeds to the gate of the last transistor, whose drain is to the positive power supply, so that's small signal ground. That's what we see here. The bulk is also small signal ground. There's no small signal variations. And then we have at the source, we have resistances to small signal ground, RS3, and the load resistance. So those two in parallel. Now we'll remove markers here. And now what we see is that each of these transistors base is a transistor primitive. And we're going to replace each of those transistor primitives with their equivalent two-port networks. So QCB, what we see is that the base is not used as an input or as an output, so that's a common base. But there's a resistance from base to small signal ground, so it's a base-degenerated common base transistor. So we replace this with its equivalent two-port network. Then the next transistor, we see that the emitter is not used as an input or an output, and the emitter is tied to small signal ground, so this is a common emitter gain stage. So we replace that with its equivalent two-port network. And then lastly, we see this MOSFET, and we see that the drain is not used for input or output, and it's connected to small signal ground, so that's a common drain, and we call that a voltage follower or a source follower. So we'll replace this with its small signal two-port equivalent circuit. So with two-port equivalent circuit here, here, and here, and then we have these resistors that basically load each of these nodes, we can get the gain. So if we look at the gain, we'll remove here, from the source voltage to the input of the first transistor, we have a voltage divider into RE1 in parallel with the input resistance of that first gain stage. Then we have a short circuit transconductance gain across the base degenerated common base into the equivalent resistance that it feeds. Then we have a short circuit transconductance gain across the common emitter into the equivalent resistance that it feeds. And lastly, we have another short circuit transconductance gain into the resistance that the last transistor feeds. And this way, we get the gain across the entire circuit. I hope this was helpful. Thanks for watching.